All right, assignment 7-1 on improper integrals. Which one of these is improper and why? So the bounds here are 0 to 9. 0 is, this is improper, because at 0 is a discontinuity, an asymptote. Is this? Well, where is the discontinuity? So if I make the denominator equal to 0, x cannot equal 2/3. And at 2/3 is in between here. So there's a discontinuity between the bounds. So it is improper. Number 3. First I have to factor it. That's going to be -5 and +1. So in between here, there's a discontinuity at +5. That's not in the between the bounds. And at -1, that's not in there. So this one's actually proper because the discontinuities are outside the bounds. This is improper because one of the bounds is infinity. So because of that, it's improper. All right, number 5, we're actually going to evaluate improper ones. So what makes this improper is at 0, there's a discontinuity. So we're going to set it up like this. We're going to call it B to 9. Or you could call it A. I'm going to call it B. And we're going to set it up as a limit as x approaches 0. And we have two directions here. And I'm going to write it calculus friendly. And it's really from the right because we can't have a negative value here. So there's no negative number, so it's only from the right where the limit actually exists in terms of that. And then I'm going to integrate it. So we're going to add 1 to the exponent. That's 1/2. Divide or the reciprocal. Oops. And then I have my bounds. Next, I'm going to substitute in. Again, this is a limit when I substitute in. So what's the limit as this approaches 0? And you can see this is 0. This is 9 times 1/2. 9 to the exponent half. This is the square root of 9, which is 3. So this is 2 times 3, take away 0. So this answer is 6. So that's the answer in terms of what's it's approaching. I know it's a little different to think about. All right, number 6. We go from 2 to 11. So from 2 to 11, what's wrong? At 2, there's a discontinuity, right? So we're going to set this up. Again, you can use A or B in terms of the situation. Recognize you can't have a negative number under a square root sign, so it's really just the limit, and we'll use A or B, from 2 from the right. Because if 2 is from the left, that's going to create a negative value there. I'm going to write this calculus friendly. So that's going to be 2, that's going to be x minus 2. And this is going to be 3 over 2, but it's a negative exponent because it's in the denominator. So negative 3 over 2. Keep that limit notation until you plug it in at the end. So we're going to add 1 to the exponent, that's negative 1/2, and then divide or multiply times the reciprocal. we still need an integration sign here that goes from a to 11. After I actually integrate, then I can draw from a to 11. Plug in 11. Now it's good to know, so here we have the limit as a approaches 2 from the right. So I'm going to plug in, I'm going to write it algebra friendly. So that's negative 2 over the square root of 11 minus 2. Subtract. Now when you subtract a negative, it'll be adding. And then when I plug in a, does this limit exist to the right in terms of it? So the answer of what's it approaching as it approaches 2 for this? And the answer is it's undefined, right? So the limit as that right there. So this answer does not converge. It diverges. Because the right-hand behavior here is it goes to infinity. There's an asymptote at positive 2. So it either goes to infinity or negative infinity. So by integrating, I see it's still there. And that this might converge to an answer. So that's 11 take away 2, which is 9. And the square root of 9 is 3. So you have negative 2/3. But this does not converge to an answer. So overall, the answer diverges. And there's no limit there. Number 7. In number 7, again, use a or b as a limit because we have an infinite limit there. So the limit as b approaches infinity, and then we change it to b. I'm going to make it calculus friendly right away. E to the negative x. The hook should be negative 1. It's 4. So what was it before? What it becomes, we need a negative 4 in front. And now we can integrate this. So it starts with negative 4. The integration of negative, this hook can go away. And then the integration of e is just copy it. And we're integrating from 0 to b. Keep that limit notation. We're going to plug in b. Now we're going to make it calculus friendly or algebra friendly. E to the negative x goes back in the denominator. And when you subtract a negative, this is going to be plus. And then you plug in 0. And then think, does this converge to an answer? So if I look here, the denominator, the right-hand behavior is going to infinity. So a number over infinity, that's 0. Here, e to the 0 is 1. So this converges to the answer 4. Because this converges to 0, that's 4. And then together the answer is 4. Number 8. If we practice it, it's going to get more comfortable. When you don't do something and it's brand new, are you patient enough to practice it? So why is this an improper integral? It's because of the negative infinity. So we're going to set it up as a limit as b approaches negative infinity. It does not matter if you use b or a. We are going to integrate this. The hook is 3, so we need a 1/3. So we have the limit as b approaches negative infinity of 1/3 e to the 3x from a to 0. And then we plug in, keep the limit notation until the end. Use parentheses. Plug in 0 first. E to the 0 is 1, so this is just 1/3. Subtract. Plug in a. And then think what the end behavior is here. Now, this is the left end in terms of what we're looking for. So 1/3 is 1/3. But when I'm thinking of this graph, which is e to whatever, the 1/3, think of what the graph does in terms of it. The right end goes to infinity, but the left end, as I plug in negative numbers in here, this is approaching 0. So this does converge to an answer. So because I'm looking at the left end, you have to know the graph. The left end is getting closer to 0, so this is approaching 0, and 1/3 take away 0 is 1/3. Number 9. Uh-oh. Where did my nice paper go? I got it. What question did I just do? I just did 8. Number 9. And I realize these questions, because they're brand new like this, that as I go one step at a time, you're following what I'm doing until you feel comfortable. When you do feel comfortable, you should try to be independent. So it's improper because of the infinite bound. We're going to write as a limit. And we're going to write it calculus friendly right away. Then keep that limit notation and just do what we normally do. So we're going to integrate it. So we're going to add 1 to the exponent and divide by that exponent from 1 to b. We can simplify this. So 3 divided by negative 3 is negative. Now I don't need the limit notation. Well, I can keep the limit notation until the very end. So the limit is b approaches this. So when I plug in b, the 3's cross out, and I'm going to make it calculus friendly. So it's negative. X to the negative 3 really goes in the denominator. So put in b for x. So this is what it looks like when you simplify it. When you subtract a negative, you're adding. And again, the 3's cross out. So it's 1 over 1 cubed. Now, what's the end behavior here? So for b cubed, this is like 1 over infinity. And so 1 over infinity, or negative 1 over infinity, this is approaching 0, so it converges to an answer. This is converging, obviously, to 1. So 0 plus 1, the value of that limit is 1. Number 10. I'm going to write it calculus friendly right away. I see that it's improper, so I'm going to write it as a limit as x approaches as b approaches infinity, and then take that out and write it as b. And then I'm going to integrate, which means I'm going to add 1 to the exponent. Oops. I'm going to add 1 to the exponent, which is 2/3, and then divide, or the reciprocal, and I'm integrating from 1 to b. Keep the limit notation, use parentheses, plug in b, and then subtract and plug in 1, and then think about it, look at it, recognize that when you plug in, this is unbounded. So what's the right end behavior of this? This is going to infinity. So it's just going to get larger and larger and larger. It doesn't converge to a number. Well, this does is negative 3 over 2. This converges. This diverges, and the limit doesn't exist, or the integral doesn't exist. The value of it. All right, number 11. I'm going to integrate from negative infinity to 0, x times e to the x dx. I think you see integration by parts here. We're going to write it as a limit. And we're going to let u equal x, du equal dx, dv is e to the x, and the integration of that is still e to the x. And then we're going to follow. Follow the rules. So for integration by parts, it's the first u times v, subtract the integration of v du. Oh, we still need the limit notation. As we do that, and we're still going from b to 0. So we have the limit as b approaches negative infinity. We have x e to the x. When I integrate e to the x, it's still e to the x, and I'm going from b to 0. So now it's fully integrated. Now substitute, keep the limit notation. Recognize it's the left end behavior we're looking at to see if it converges to an answer. So first I plug in 0, e to the 0, and e to the 0, and 0. So 0 times anything is 0 minus e to the 0, so that's negative 1. Subtract. Now plug in b. And then we have to think about it because it's the left end. So if you think of like e to the b and e to the b, the exponential function, the left end is approaching 0. So when I look at number 11, this is approaching 0, so the answer is negative 1, take away 0. And 0 times infinity times 0, so this is all 0, and this is approaching negative 1. So the answer is negative 1. Number 12. The limit as x, or number 12. All right, let's write down the question first. From 0 to infinity. And now let's just look at it just for a second. So this is going to be a limit question. The limit as x approaches, you can call it a or b. Usually the bottom one's b, the top one's a, but you can do what you want in terms of that. I'm going to write it calculus friendly. Again, it looks like it's by parts to be able to integrate it. So u is going to be x and du is going to be dx. E to the negative x is dv. And so when I integrate it, it just needs a negative e to the negative x. So when you integrate, the hook is negative, and then you copy. So that's what it is. The limit as x approaches a. So the formula is u times v minus, we're still integrating from 0 to a, dv v du, right? So v du. So the hook that we need is there. So we have the limit as x approaches a, negative x, e to the negative x. This is going to be negative e to the negative x because you're copying it, and it goes from 0 to a. Keep writing the limit notation. We're going to write this calculus friendly so you can see it. So first I'm going to plug in a. Again, I'm going to write this calculus friendly so you can see it. When I plug in 0, 0 times anything is 0, and then e to the 0 is 1, so that's just negative 1. So as x approaches a, did I really say that? As x approaches infinity, all right. So if I look here, both of these are approaching infinity, but which one approaches faster? And because the bottom is more powerful, this is 0. The bottom is more powerful, this is 0. And then when you subtract a negative, and so the value of it is 1. Practice, right? And see, obviously, if you don't have a fraction, it's not going to converge to an answer the same way. If you have a fraction and you see the bottom is more powerful, that's what converges to 0. That allows us to get an answer. Number 13. E to infinity, 1 over x times ln x to the 4th. So step number 1, we're going to write it as a limit. You can use b or a. E is a number. I'm going to write this so I can integrate it. So we have 1 over x and then ln x to the negative 4. The hook is 1 over x, so it's good. Keep writing the limit notation until the very end. And the end will either have an answer or the end will be it diverges. All right, we're going to add 1 to the exponent and then divide by that exponent. I'm going to write it calculus or algebra friendly so I can see if it converges or diverges. So a negative exponent means it's going to go in the denominator. When you subtract a negative, it's positive. And then look carefully. Does it converge to an answer? So to infinity. So if I look here, the right end behavior for ln it does go to infinity. And so the bottom is more powerful than the top. So this approaches 0. Here, ln e is 1. So 1 cubed is 1. So this whole answer is just 0 plus 1/3, which is 1/3. Are you ready? It's okay. Do you know what sometimes you have to do? Is we'll go through this, and you go back to question number 1 or 2. I know, time is tough, but once we go through the homework, if you went back and then practice over again what you're now starting to learn and become independent, that's really what we want, right? All right, so you see why it's improper. So we're going to write it as a limit as b approaches infinity, and just write it from 0 to b. I'm going to write this as e to the x plus 3 to the negative 1 times e to the x. Well, you know what? Duh. I'm not going to do that at all. So it's a logarithm. First thing you should check, right? So when you take the derivative of the bottom, does it match the top? Yes, it's a logarithm. So we're going to write a limit as b approaches infinity, and we're going to integrate it. And it's a logarithm. E to the x plus 3 from 0 to b. Keep the limit notation. Now we're going to substitute in b. Subtract, plug in 0. E to the 0 is 1, so it's ln 4. And then think, does this converge or diverge? And so as this goes to infinity, it does not converge. I don't have that fraction. I don't have that thing. The right end behavior is going up forever, so it does not converge to an answer. So number 14 diverges. And that's it. Number 15. Sine's a tough one because it oscillates, right? What's the right end behavior there? It doesn't have one, right? It doesn't converge to something or the left end behavior as it goes to infinity or negative infinity. It oscillates. So it doesn't exist, the right or left end in terms of that. All right, so we're still going to set it up as a limit as whatever letters we use, b. Then I'm going to integrate it. So integration of sine is cosine, negative cosine. And then plug in, so you have the limit as b approaches infinity, and you have negative cosine b, subtract a negative, and it's adding cosine 0. Now the value at cosine 0 is 1, but this, the right end behavior, does not converge to an answer. It just oscillates up and down. It doesn't come together to a number, so this whole thing diverges. Number 16. I'm going to create a limit. How about a? Or do I create a limit? What's wrong here? So at 0, it's actually undefined. That's the problem. So why is it improper? Because ln 0 is undefined. So you want 0 from the right side. What technique we're going to use to integrate this is by parts. U has to be ln x, and du then is 1 over x. dv is x, so v is the integration of that. And then use the formula. So we have the limit as a approaches 0 from the right. And it's u times v, so it's that, times x squared over 2, u times v, subtract v du. And again, I'm going from a to 1. All right, so the limit as a approaches 0 from the right. So we have ln x times x squared over 2. We have x makes the x squared just an x. So it's just x over 2. So I add 1 to the exponent and divide. So that's x squared over 4. And again, I go from a to 1 for all of it. Next, keep the limit notation as a approaches 0 from the right. So we're going to first plug in 1. So ln 1 is 0. So 0 divided by 2, that's 0. So I have negative 1/4. Subtract, use parentheses. We're going to plug in a. So we have ln a times a squared over 2 minus a squared over 4. So what's the limit? And again, the right and left only if it's undefined. So the right end behavior here, this is getting closer and closer to, this diverges, right? Number 16? No. Oh, we get that. So we can write this. We have negative 14. This is 0. And so this in the middle, you can use L'Hopital's rule. So we have negative 14, and when you plug in 0, this is 0. When I plug in 0, it's still undefined, and from the right, it's an asymptote. But we can simplify this using L'Hopital's rule, because it is, we could write this as a to the negative 2 underneath, and then it's, from the right, it's negative infinity over infinity. It's indeterminate. So I can take the derivative there. So that's 1 over a, and this is negative 4a to the negative 1. Or sorry, subtract 1 to the negative 3. Simplify that. So the a and the negative 4 go here, but this actually goes above. So if I simplify it, it just becomes a squared, and the a's simplify out. So this actually all becomes 0. So the answer is negative 1/4. That's good stuff. Number 17. Three more like this, and then the rest are kind of like review questions. So we're integrating from 0 to 3. I'm really proud of you that you're sticking with this. I'm going to factor this. It's a difference of squares. And for a difference of squares, notice that positive 3, that's what makes it improper. So I have to do the limit as x approaches a. Sorry, as a approaches 3. And we're going from 0 to a. And then we're going to do this by separating them. So we have a, x plus 3. We have b, x minus 3, and that's 6 over this. To create common denominators, we're going to multiply by x minus 3. We're going to multiply by x plus 3. And then we're going to let x equal 3. So that's 6b equals 6, so b equals 1. We're going to let x equal negative 3. That's negative 6b is equal to that, so b is negative 1. So we're going to take these values. Oops, this should be a. So a is negative 1. and b is 1. So come back here. The limit as a approaches 3, and we have a is negative 1 over x plus 3, b is positive 1 over x minus 3. Keep the limit notation as you are integrating. So this is negative ln x plus 3. Subtract or add ln x minus 3 from 0 to a. And then we plug in a. Subtract, plug in 0. And now we have to look at it. And does this converge or diverge? So at positive 3, 3 take away 3, ln 0, this diverges. There's an asymptote there. As it approaches 3, right, it goes to negative infinity as it's going. So this answer diverges. It does not converge to an answer, right? That's a lot of work to just to say the word diverges, isn't it? Pretty good. All right, number 18. In number 18, we are integrating from 0 to 9. I want you to notice that positive 1 is in the middle. So we have to first go from 0 to 1. And then we have to go from 1 to 9. So we have to set up as two integrals. So the first one is 1 from the left. So the limit as a approaches 1 from the left would be from 0 to a, calculus friendly. And then the second limit will be as b approaches 1 from the right. And that would be from b to 9. Again, calculus friendly. All right, so now let's just do what we know we can do. So we're going to add 1 to the exponent, and then instead of dividing the reciprocal, and that goes from 0 to a. We're going to do the same thing here. We're going to add 1 to the exponent in the reciprocal. This one's going to go from b to 9. And now we're going to substitute in and see if the limit exists, if it does, or if it converges to something, or if it diverges something. So when I look at 1 from the left, when I plug in a, subtract, plug in 0, plug in 9, take away 1 is 8, subtract, plug in 0, plug in b, all right, so as a approaches 1 here, this exists. It's not undefined. It's not in the denominator to make it 0. It's no longer there. So when I plug in 1, I actually have a value there. This is 0. Done. So I'm left with negative 3 over 2 and negative 1 to the 2/3. On this side, if I plug in 1 here, 1 take away 1 is 0. It's not undefined. It's not an asymptote. It's just 0. So that's done. And then I'm left with 3 over 2, 8 to the 2/3. And that's a good answer. I don't even want to pretend. We could simplify it, but I don't want you to. That's a great answer right there. So it does converge to an answer. Number 19. Last one like this. It's going to be okay. That's how you learn it, right? It's by practicing. We're going to write this right away, friendly. I want you to notice that there's a discontinuity at positive 1. It's in the middle. So we're going to set this up positive 1. So 1's going to go the limit as a approaches 1 from the left, goes from 0 to a, plus the limit, we'll use b from the right, it's going to go from b to 4. And if you want, you could do this ahead of time, 0 to 1, x minus 1 to the negative, plus 1 to 4. And that's what we're doing. So from 0 to 1, 1 to 4, right where the discontinuity is, and then we're doing limits for here because it's improper. So 1 is going to be a and 1's going to be b. That's the hard part. Now just think what we normally do. So we're going to add 1 to the exponent and then divide, and that goes from 0 to a. We're going to do the same thing here. So it integrated the same way, but this one goes b to 4. We're going to write this calculus friendly so you can see it. So I'm going to plug in a, subtract a negative. I'm going to plug in 0. I can already see what's happening here. Again, I'm going to plug in b, subtract a negative. I'm going to plug in 4. And then when you plug in 1, it is undefined here. There's an asymptote there. It does not converge to an answer because it's in the denominator. So before, when I integrated, it was no longer in the denominator, so it converged to something. Number 19 diverges. So when I plug in 1, it's still undefined. It's still improper. I can't, does not converge to an answer. Woo! I don't blame you to press pause. Take a little break. Here we go. Y is less than or equal to 1 over x squared. Y is greater than or equal to 0. X is greater than or equal to 1. So first of all, sketch the region that you see. All right, so we have y equals 0, x equals 1. Plug in 1 and the answer is 1. And then what does 1 over x squared? What's happening at 0 is an asymptote. So this is going to infinity on one side, and then it comes down to like this. And so the area that we're looking for when x is greater than or equal to 1 is this area to this area. So in between here, it's less than the curve. So it's less than the curve, it's bigger than 0, and then at 1 is that vertical part that shows this is the area that goes on forever like that. So that's what we're looking at. B, find the area of that. That's an integration question that goes 1 to infinity. I'm going to write it calculus friendly. I need to set this up as a limit. And then to integrate it, I'm going to add 1. Oops. I'm going to add 1 and divide by negative 1. I'm going to write it algebra friendly so I can see if it diverges or converges. So that's going to be over x. When you subtract a negative, it's adding. That's over 1. What happens here? So this, as this approaches infinity, because the bottom is more powerful than the top. Oops, it shouldn't be. Where did x come from? This should be 1 over a. There you go. Okay, so because the bottom is more powerful than the top, because the bottom's going to infinity, this is 0, and that leaves me the answer, which is 1. All right, 20C. Let me do it up here, maybe if I have room. So C says, find the volume revolving around the x-axis. All right, I'm not going to have room, so I'm going to go here. So 20C, volume is this. And inside would be the curve, which 1 over x squared, or x to the negative 2, and that goes from 1 to infinity. And that's what you would solve. So you can see we can use A or B. Together, this is x to the negative 4. So I'm going to add 1 to the exponent and divide from 1 to b. At this step, I'm going to write it calculus friendly, or algebra friendly. So this is going to go in the denominator. So we have b 3b cubed in the bottom. Subtract a negative. Put in 1. And then the limit as, why do I write that down like that? Can you write it down properly here? The limit as b approaches infinity. The limit as b approaches infinity. The limit as b approaches infinity. I can do better. So as b goes to infinity, the bottom is more powerful. This is 0. This is 1 times pi, so the answer is just pi. Oh, what happened to the 3? There's a 3 down there. So that when you plug in there, that 3 is down there. So it's actually 1/3 pi, or pi over 3. 20D. Here's my chance. I can do better. 20D says find the volume revolving it about the y-axis, if possible. So let's look at the picture again. This is going to be the cylinder, the shell method. Where did I put it? All right. So if it's around the shell method, I have to go right, subtract left in terms of understand. So I'm still, in terms, the formula starts with 2 pi, and I'm going to still go from 1 to infinity. And then what's the radius and what's the height? So the radius is when you go right, subtract left. So it's going to be the x coordinate, subtract 1. Or just the x coordinate in terms of that. So from 1 on, it would just be the x coordinate. That would be that width. And then the height is the curve. So it's just the x times 1 over x squared. So this is the radius, and that's the height, dx. And that's the formula for the shell method. So this simplifies to just 1 over x, or x to the negative 1. This is improper, so we're going to write it as a limit as b approaches infinity. Fly right there. So it goes from 1 to b. Now, x to the negative 1, or 1 over x, when you integrate that, that's a logarithm. So that's ln, and that goes from 1 to b. Keep that limit notation. Plug in b first, subtract, plug in 1. So ln 1 is 0. Here, we don't have a fraction. We don't have something in the denominator or something. So this goes to infinity. So this diverges. It does not converge to a number. because the right-hand behavior of a logarithm is infinity. All right, 21. See how many more we can get done here. Sketch a graph for f at x given the following. So we have f at 0 equals 1. F at 1 all right, this is now a review question. So f at 0 equals 1. F at 1 doesn't exist, so it's like a hole. F at 2 equals 2. So let's just do that to begin with. So f at 0 equals 1. F at 1 doesn't exist. F at 2 is equal to 2. Got it. Then it says the derivative. So when it's less than 0, the derivative is less than 0 for between when it's less than 1 and between 1 and 2. The derivative is greater than 0 when it's bigger than 2. So we have a minimum at 2. Keep going. What's the next part that we're asked? The second derivative. So it's less than 0, so it's concave down when it's less than 1. It's greater than 0, concave up when it's bigger than 1. So we have a point of inflection here. And it's concave down and so on. So we can see it decreases. So it decreases and concave down. So it decreases, concave down. And then at 1, it continues to decrease, but it's concave up. So it goes all the way to 1, right? And then it doesn't exist. It continues to decrease. This is concave down, but it's now concave up. And it continues to be concave up, and it keeps going. That was a good one. So it decreases. It doesn't exist here. It's concave down. It's concave up and continues to decrease. There's a minimum. And does this match this and this and this, right? Double check, and it does. All right, number 22. All right, 1 second.